This is our first PowerPoint in Unit 4, and it is a type of equilibrium. It's called Ksp, which stands for Solubility Product, and it involves the solubility of what we previously called insoluble ionic compounds. You'll find that nothing is truly totally insoluble. All right, so everything has a limit on its solubility. Even something that you think of as very soluble, like sodium chloride, you can't just put an unlimited amount in. And it turns out that solubility itself is an equilibrium. So as soon as you reach the saturation point, there is an ongoing dynamic equilibrium between the dissolution process and then recombining of, in this case, the ions to form the original compound. So again, just as all equilibrium, when it reaches equilibrium, it's dynamic. It doesn't just stop. So we gave you this table of solubility rules, and we kind of oversimplified ionic compound solubility, saying some things are soluble and some things are not. It turns out that all of them have a degree of solubility. Now, the solubility may be so minimal that it's extremely hard to detect, but for almost everything, we can detect minuscule amounts that dissolve. And so that's what this lecture is about. There are equilibrium constants for slightly soluble ionic compounds, again called Ksp. All the rules for equilibrium apply to this. There are a couple of kind of unique things. Otherwise, you treat it the same. So let's look again at an equilibrium equation for solubility of, or the dissolution of, in this case, lead 2 sulfate. And lead is one of those cations, if you remember anything at all about the solubility rules, that lead can tend to make things insoluble. So even though sulfates are usually soluble, this lead is making it not very soluble. So let's first remember how we set up an equilibrium constant expression. So remember, it is concentration of products over concentration of reactants, right? Each of the concentration raised to some power, and that power depends on the coefficient in front of the substance. I also want to remind you that pure solids and liquids, let me get rid of that, are not included in equilibrium constant expression. So there will never be a denominator, okay? There will never be a denominator in a Ksp expression. So I would actually write that down, make sure you don't mess that up. Never is there a denominator. Why is that? Because the reactant, this isn't really a chemical reaction, but the starting substance, we're going to call it a reactant for argument's sake, is always a slightly soluble salt, which we call insoluble, okay? And so it's, in all effect, it's a solid, an insoluble solid, even though we know it's slightly soluble. Anyway, so the equilibrium constant expression will never have a denominator. So the rest of the properties of any equilibrium are the same. Just like all equilibrium constant values, the only thing that changes the value of an equilibrium constant is temperature. I'm going to say that again. That's really important. The only thing that will change the value of an equilibrium constant is temperature. That is the only thing. Now, we've talked about Le Chatelier and shifting a reaction left and right. None of that, nothing that has anything to do with Le Chatelier changes the actual value of K. Only temperature does. So as with all equilibrium constants, the larger the value of K, the more product is formed. Because remember what K is, right? It's products over reactants. So The larger the value is, the larger the numerator or the amount of product is. Now, toward the end of this PowerPoint, we're going to be talking about solubility. I want to just kind of red flag you that solubility is not the same thing as Ksp. For some reason, students get these mixed up. They're totally different. So, all right, just to give you an idea of solubility, product equilibrium constants, they can get really, really small. And I've had students in the past say, can this be right? I've actually seen some that are on the order of like minus 70 or even more negative than that. So that gives you an idea of the minuscule amount we can detect dissolved. But they're all pretty small, okay? So just kind of you get a feel for the magnitude. All right, so let's get a little bit of practice in writing equilibrium constant expressions for slightly soluble salts. So if you haven't already, I would encourage you to try these on your own. This is also good review for your final exam because look at this. You have to remember how to write formulas from names, and that's important. So let's kind of go through that, and I'll walk you through all of them. Magnesium. So anytime you're talking about an ionic compound, writing the formula is a two-step process. The first step is writing the individual ions with their charge. Carbonate is a polyatomic. So you want to combine the two ions so that the overall charge is 0. And since they have the same charge, I'm just going to combine them into 1-to-1 ratio. Once you know what you're dealing with, the next thing you want to do is write out the equilibrium for the dissolution. Now remember, if you're asking for a Ksp value, that means a substance is only slightly soluble. So when you write the equilibrium process for a Ksp, make sure that you show the charges on the ions. Otherwise, it won't be correct. Then you want to write the Ksp expression. So concentration of products, again, don't leave these charges out. Now, coefficients are 1 in this case, so there's no exponent. And again, there's never a denominator, right? Because the reactant is always a solid, which is not included. Go ahead and try the next two on your own, and I will also work them out on the next page. The second one was iron 2 hydroxide and calcium phosphate. Actually, I want to review real quick writing these formulas in case you're rusty on it. So the Roman numeral tells us the charge on the transition metal. Hydroxide is a polyatomic ion with a charge of -1. So when we crisscross or combine them in such a way that the overall charge is 0, that's what we get. And calcium phosphate gives us a formula of Ca3PO4 2. And so let's go ahead and write the equilibrium for the dissolution of these. Now, see, in this case, in both cases, we're going to have a coefficient other than 1, so that'll make it a little more interesting. I'm going to do my equilibrium upside down here. So I have 3 calcium ions and 2 phosphate ions. Alrighty, so the Ksp expression for the iron 2 hydroxide is concentration of iron ion times concentration of the hydroxide ion squared because of the coefficient. And let's see, Ksp for calcium phosphate, concentration of the calcium ion cubed times concentration of the phosphate ion squared. All right, so hopefully you'll practice a few more of those. As is the case with most chemistry concepts, there are several iterations of this type of KSP problem, several different ways to ask the question. And so just trying to expose you to many of the different types of problems you might see. You might be asked, or will be asked most likely, to predict whether or not a precipitate will form in a particular solution. And what you're going to want to do, then keep in mind that any equilibrium constant, the value of that means that the system is at equilibrium, right? And in the case of KSP, what does that mean? That means the system has reached the maximum solubility. So whenever K, or whenever the concentrations, the product of the concentrations reaches the value of KSP, that means no more of the substance will dissolve. So let's say that you're given concentrations of the individual ions and asked, hey, will a precipitate form or will it all dissolve? You're going to have to use Q. Now remember, Q has the same formula as K, but Q, the concentrations used for Q, can be concentrations obtained at any point. They do not have to be concentrations at equilibrium. And Q is very useful to see whether or not a system is at equilibrium. So just kind of to remind you, if you get a Q value that's smaller than K, that means you're not quite at equilibrium. And in the case of a KSP, if Q is smaller than K, it means that more will dissolve, okay? If Q is smaller than K, and for KSP and QSP, if Q is smaller, that means more can dissolve. That means you can make more product, more can fit in. If Q is larger than K, that means there's too much ion in solution. You've exceeded the KSP value, and it's going to go in the reverse direction, which means you're going to make more of the undissolved stuff. And this, remember, an insoluble solid is what a precipitate is. So if they're asking, will a precipitate form, they're asking you, will the reverse reaction proceed or predominate to make the insoluble solid fall out. So here's an example of a problem just like that. Actually, this one's more complicated, of course. And this is actually, this version of problem might be one that would be good for a free response question. It's kind of involved, and you definitely need to practice this type of problem. It's tricky. All right, so in this case, they're mixing two different substances together. So there's several things you have to do. The first thing you have to do is, this is a chemical reaction. Now, you probably won't be asked to write out the chemical reaction. I'll explain that later, but I just want you to see what's going on. When you mix two ionic compounds, I don't know if you remember this from your chemical reactions, but you get a double replacement reaction. And double replacement is when you mix any two ionic compounds together and they switch partners. So you can, let's just say, switch the cations around. So what happens when you do that? Well, calcium ends up with fluoride and sodium now ends up with nitrate. And why are they doing that? Because we started out with two reactants that were soluble. Okay, that's what the aqueous means. Remember, soluble in water, dissolved in water. But one of the products we have formed is a solid, is insoluble. And anytime you have an ionic compound that's designated with an S, that means it is a slightly, we used to call it insoluble, but now we know it's slightly soluble salt, and that means that it's going to have a KSP that determines how much of it can dissolve. So let's reread the question again. They're saying when we mix these items together, let me get a different color pen. When we mix these two compounds together, does a precipitate form? Okay, well, if any precipitate formed, what would it be? It would be the product that is insoluble. So I've written this out for you. Let me write it again down here, but sometimes you might have to write that out yourself. So here is the Ksp equilibrium equation that we're going to be working with. All right, and so the Ksp, as always, right, concentration of the products. Now fluorine has a coefficient of 2, so we got to make sure that becomes the exponent. So here's the expression for Ksp. Now the problem, it gives you a Ksp, and so that's important to notice that. So when I said you don't usually have to write out this reaction like I have here, because whatever they give you a Ksp for, and they'll usually tell you what it is. They'll usually say, okay, calcium fluoride has a Ksp value of that. They're telling you what the insoluble solid product is. Okay, so you usually don't have to think through it on your own. All right, so how do we figure if a precipitate's made of this stuff? Well, remember, we've got to figure out whether or not these concentrations that have been added are going to exceed our allowed Ksp value or not. So we're going to use Q and see whether or not we're past the Ksp value. All right, here Q has the same exact formula as K, but we can use the concentrations we have right now. So I told you this was a complicated problem. Here is making it even more complicated. How many of you are going to be tempted to just use these concentrations? No, no, no. Okay. Why can't we use those concentrations? Okay, what I'm getting ready to say is really, really, really important. Anytime you mix together 2 or more different things, you have effectively diluted every substance. Okay? So even though our calcium nitrate started at 0.3 molar and our sodium fluoride started at 0.06 molar, once we mix these two together, we have increased the volume for both of them, and they're both going to get diluted. All right, so we need to figure out the concentrations of the mixed together solution. So that, remember, the concentration is molarity, right? And molarity is moles per liter. So we got to figure out the moles we started with and divide it by the total volume of the two mixed together. And that's what I've done down here. So moles, if you're dealing with molarity from a solution, is always, remember, molarity is moles over liter. So if we rearrange that to solve for moles, moles is molarity times liters, right? So that's what we've done here. Molarity times liters of the calcium nitrate. There are the moles. And then to get the new concentration of calcium ion, we take the moles that we just calculated and divide it by the total volume of both solutions we mix together. So that'd be 0.1 liter plus 0.2 liters. And here is the new concentration of the calcium ion. We do the same to calculate the concentration of fluoride. And that was volume times molarity. And that gives us the moles of fluoride. Again, divided by the total volume of the two solutions. Now, I always encourage students to write out the expression for the Ksp or the Qsp because it's so common. If you do all this extra work, like calculate the new concentrations, it's so common for students to just say, okay, I'm going to multiply these two concentrations by each other, and I'm done. And they totally forget there might be an exponent in one of them. So it's really important to have this generic expression right near you so that you can plug into it and make sure you don't forget exponents. All right, so now go ahead and do that math. And the Q value we get is 1.6 times 10 to the minus 4. What was the actual K value? And I really make a huge mess when I write. So here, now you can see, why is it not erasing anymore? Interesting. Okay, now you can see the original K value, and we're going to compare Q to K. All right, so Q is a lot larger than K. Okay, it's only the minus 4, K is the minus 11. So we have exceeded the solubility. There's way too much ion in there, which means it's going to go to the left and make more precipitate, okay, until the Q value gets much smaller than it is. All right. There are a couple Le Chatelier type effects on a Ksp problem that you should be aware of. And it's also a good review for the final because Le Chatelier is an important concept. So let's talk about lead chromate. Here's our lead, which seems to make a lot of things insoluble. And so here's the equilibrium equation for the dissolution of lead chromate, lead 2 chromate. And we could easily calculate what the solubility is in pure water. But then there's an iteration of that problem, or there's a modification of that problem where it might say, how much lead chromate will dissolve in a solution that has a certain amount of chromate ion already in it? You may be able to intuitively realize that if you already have some of the ion that forms when it dissolves, that less of this is going to dissolve. That is called the common ion effect. So, and there are some problems, actually calculation type problems you can do on that. But the bottom line is, if you're trying to dissolve something into a solution that already has one of the ions it's going to form, not as much. Okay, the solubility of the insoluble stuff will be lower. Not as much will dissolve. And so here's kind of in clearer words. Solubility decreases in the presence of a common ion. And you can explain it in terms of Le Chatelier. So Le Chatelier says, if you do something to disturb an equilibrium, in this case, if we add more of one of the ions, what's going to happen? It's going to try to get rid of what you just dumped in there by shifting the reaction to the left. I really like this example. This is a real-life example of Le Chatelier type effect on dissolution of something. So it turns out that statues, marble, limestone, things like that, are primarily made of calcium carbonate, which is a slightly soluble ionic compound. And so it turns out, you've probably seen this or heard this, that acid rain is kind of ruining famous old statues, kind of eating away at them. And intuitively, I know that you think of acid kind of does that to a lot of things, but it's interesting to look at the exact chemistry that's going on. So look at the equilibrium for the dissolution of calcium carbonate. I'm going to turn this off. There we go. And if we add an acid, so there's acid present in acid rain, obviously. If there's any type of base in one of the if either one of the ions that are formed when a slightly soluble salt dissolves is basic, and we know anything with a negative charge can be basic, that base will react with the acid, right? Or you can just write H+, right? Because any acid is a source of H+. And so we could end up with this acid. Well, according to Le Chatelier, what does that do? It takes away one of the products. Okay, it removes one of the products. And so according to Le Chatelier tries to undo anything you've done to disturb an equilibrium. So we've disturbed this equilibrium by removing one of the products. So Le Chatelier is going to react by shifting the reaction to the right to make more product that we've removed. And so I want you to think of this from the perspective of the poor statue. These statues are made of calcium carbonate. When the acid rain comes, it makes the solubility of the marble or the limestone go up. Okay, so we don't want the limestone or the marble to dissolve, but the acid rain makes it more and more soluble, and that's what's going on. All right, so it will affect, acids will affect only certain solubilities. Let's look at one that it doesn't affect, bromide ion. Okay, it's got a negative charge. I told you anything with a negative charge could possibly act as a base. But what happens when, for example, we take the bromide ion and react it with hydrogen ion in an acid-base reaction? You get HBr, right? That is a strong acid. Okay, so if you didn't memorize your strong acids, and I realize you have access to everything on the next test, but at least have a table of strong acids and bases present at your fingertips, okay? As well as a solubility chart. So what's a definition of a strong acid? A definition of a strong acid is it completely dissociates. It doesn't exist in the intact molecular form. It exists 100% in the separated ion form. So this reaction is not going to happen. So the bottom line is if there's a base present when a slightly soluble ionic compound dissolves, that base will react with an acid only if it makes a weak acid. Okay? If it makes a strong acid, it's not going to happen. Let's look at another one. Let's combine, we all know hydroxide's a base, right? And let's combine it with an acid. What do we get? We get water. Well, we know water is not a strong acid, right? It's very stable. So that's going to happen. That will happen. And so copper hydroxide, copper 2 hydroxide, will become more soluble if acid's dumped in because the acid's going to remove one of its products. We are getting close to being done. All right, this in my opinion, is the most important type of KSP problem. So I really want you to know everything in this lecture, but if you're short on time, this is the one that is the most important. This is probably more likely than the other one to be a free response question. All right, so the other problems we've done so far have either calculated Q and compared it to K, or just writing equilibrium expressions. But in this case, you're actually asked to calculate the solubility. So first of all, what is the solubility? The solubility is the molarity of the slightly soluble salt that dissolves. So it's the concentration of calcium hydroxide in this case that actually dissolves. That is solubility. Now, so look at the stoichiometry. We can't really directly calculate the concentration of the slightly soluble salt that dissolves. But since there's a 1-to-1 relationship stoichiometrically of the calcium hydroxide and the calcium ion, we can figure out the concentration of calcium ion, and that will equal the solubility because there's a 1-to-1 relationship. So the bottom line is solubility is X in your ICE table. So if you were writing an ice table, and we're going to do one for example, you would give X for calcium ion and 2X for the hydroxide ion. When you solve for X, that is going to be your solubility. So let's go ahead and work this one through. All right, so here is our equilibrium. Here is our Ksp expression. Again, please, please, please write the generic Ksp expression before you plug in numbers so that you don't forget any exponents. Then we're going to do our ice table. Now, the reactant, the slightly soluble salt, is a solid. It has no effect on equilibrium, so just put a big old X through that column. Again, unless you're told otherwise, the initial concentration of products is 0. Okay, change, as most of the time in products, it's plus, right? And I don't know why there's S in this table, SX, whatever you want to call it, X, 2S. So here are the equilibrium concentrations. Now you go back and plug them into your expression for the Ksp. That's S times 2S squared. Now listen to me really, really carefully. You're going to feel like you accounted for this 2, this coefficient of 2 twice. Notice, pay attention that you have 2 inside the parentheses because to account for the mole ratio. And then you also have an exponent of 2 because that is what Ksp tells you to do, is make the coefficients exponents. So you have accounted for this coefficient, as you will all the time, twice. So if you had something, let's say we had 3 hydroxys that were formed, the expression would then be 3x, if we called, 3x cubed. So you're always, if something has a coefficient in front of it other than 1, that coefficient's going to be in front of the x inside the parentheses, and it's also going to be an exponent. It can be really, really tricky. So so now listen to me again really, really carefully. What is the product of these? What students tend to leave out is 2s squared is 4s squared. I don't know how many students write this, leave it as 2s squared. That is not right. You have got to square the s and the 2. So that together gives you 4s cubed. Now 4s cubed is the most common Ksp expression you're going to encounter. If you ever work a problem and you end up with, what happened here? You end up with 2s cubed, you have done something wrong. Okay, so 4s cubed, really, really common. So now 4s cubed, we set it equal to, this keeps wanting to change on me, we set that equal to the Ksp value, which they have to give to you. So 4s cubed equals 6.5 times 10 to the minus 6. And I need my magic eraser again. All right, and let's go ahead and simplify that then. So 4s cubed equals, if I didn't write so big, it wouldn't be a problem. 6.5 times 10 to the minus 6. First thing you need to do is divide both sides by 4. Okay, so you want to divide by your coefficient, and then you're going to get s cubed is 6.5 times 10 to the minus 6 divided by 4. And then you're going to take the cube root of both sides. Now I want to remind you, so find the cube root on your calculator right now, but I also want to remind you that you get the identical answer, same answer. Instead of, if you can't find your cube root, or if it's easier for you, you can raise it to the power of 1/3. Just like in square root, you can raise something to the power of 1/2, and you're going to get the same answer. Alrighty, so we are now going to combine finding solubility with the common ion effect. And so what we just did is we calculated the solubility of calcium hydroxide in pure water. And now they're asking, what is the solubility of calcium hydroxide instead of in pure water in a solution of 0.1 molar calcium nitrate? This is a higher level question. It's not going to be a major part, but you're going to have some higher level questions on the test. So the first thing you do if there's something already in the solution besides pure water is you ask yourself, is there a common ion? Are one of these ions in the stuff I'm trying to dissolve? Or does anything in that react with what I'm trying to dissolve? So reactions mean they're going to be like if they add an acid, then you have to say, is that going to react? In this case, calcium nitrate, when it dissolves, is going to make calcium ion and nitrate ion. And it turns out calcium is the common ion, right? That's what we're going to try to dissolve. And so now look at how the ice table changes. Here's the equilibrium. So you don't put the calcium nitrate as part of equilibrium. It's not. Calcium nitrate's completely soluble ionic compound, so it has nothing to do with the equilibrium. However, notice that normally the products are, there it goes again. Normally the products, their initial concentration is 0. If you have a common ion present, the initial concentration is the concentration of that common ion, in this case 0.1. Okay, and that's the only difference for a common ion. So then the change, of course, is always related to the stoichiometry, the coefficients. So we're going to call concentration of calcium ion S. And since there's a coefficient of 2 in front of the hydroxide, that's 2S. Then just add everything up. And there we go. So now the expression for Ksp, which I always like you to write generic first, right? So that you don't forget exponents. And in this case, we have an exponent for the hydroxide. So now I'm going to go ahead and plug in the values. Calcium is 0.1 plus S. Hydroxide is 2S. Don't forget, that is squared. And all that has to equal the given Ksp value, 6.5 times 10 to the minus 6. And now we've got to solve for S. So here it is again. Now, we've talked about X before. These type of problems tend to use S just because of solubility, but it's the same thing as X. So we're going to, in most cases, it's going to be perfectly fine to neglect X. Now remember, you can only neglect X when it's added or subtracted to a larger, from or to a larger number. And you have to ask yourself, is S or X, do you think it's safe to neglect it? Look at the value of K. Almost all Ksp values are very, 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 very small, which means that X is very, very, very small. And so, let's erase that there. And so the X or the S that you want to neglect is the one that's added or subtracted to a larger number. Okay, obviously you can't neglect an X or S that's multiplied by something because then everything will be 0. All right, so here is the simplified after we've neglected X. Now, if you didn't neglect S, you would just end up with a quadratic equation. And if you know how to solve quadratic equations, that would give you the right answer. So you could do it that way. It's just a pain in the rump. So now let's be careful to solve this correct. You want to do, if you have an exponent, you want to do that first. So 2s squared is 4s squared. And that is multiplied by the 0.10. So let's simplify that. That means we have 0.4s squared. So now I'm going to just move it down here. 0.4s squared equals the original Ksp value. So that's 6.5 times 10 to the minus 6. I'm going to divide both sides by 0.4. And that then tells us that S squared is 6.5 times 10 to the minus 6 divided by 0.4. And now you have to take the square root of both sides. And so the bottom line is the answer we get here is that X, or solubility, is 4 times 10 to the minus 3. Now, what did we get for the solubility, or for X, when there wasn't any common ion? If you go back on the previous 2 slides ago, the solubility was 1.2 times 10 to the minus 2. So it is a lot less soluble in the presence of a common ion, which is what you would expect. If you look at the equilibrium and you dump in, you add more of one of the ions, in this case calcium, Le Chatelier says that it's going to try to undo what you just did. It's going to try to get rid of that extra calcium you just added by shifting left, making more precipitate, which means since you're making more precipitate, that means it's being less soluble. And that is it for KSP. It's a hefty topic, isn't it?